this, I would say, is an example of using fundamental identities. As I'm looking at secant squared minus 1, yeah, I could go back to my Pythagorean identities right here, and secant squared, see here, if 1 plus tan squared equals secant squared, what does secant squared minus 1 equal? Tangent squared, right? If I took a 1 away to this side, then I would have secant squared minus 1 is tan squared. So, if tan squared theta plus 1 equals secant squared theta, then tan squared equals secant squared minus 1. So I can substitute here for the secant squared minus 1. That's tan squared. Okay, now I got to make the right-hand side is sine squared. So let's write these in terms of sines and cosines to see whether we can get some things to cancel and leave sine squared. Like how could I rewrite tan squared? Tan squared equals, what's that? It's sine over cosine, right? Tangent is sine over cosine. So this is sine squared theta over cosine squared theta, right? And how about secant squared? Secant squared is, yeah, so we have a 1 over secant squared, so that equals cosine squared. Right? This is this. This is this. Right? If it's a secant squared in the denominator, then it's a cosine squared in the numerator. And now your cosine squareds cancel. Right, so we worked on the left side, the more complicated side, and we made it look like the right-hand side, and check. We verified the identity. That means this is true for all values of